Now we get into the mathematics. There should have been something in you that was a little bit dissatisfied with, we'll use the mean point and just eyeball it. Because that doesn't seem like that would always, then we'd have to decide whose eyeball is better for which one's best. Is there a best line of best fit? Yes. How do we find that? Well, we use something called the least squares regression line. And it's going to be very similar to the idea that we did for variance. When we had data and looked at variance, how much it was away from the data, remember we measured how far it was away from the average and squared it so that being above or being below the average was given an equal weight? We're going to do something with a line of best fit. We're going to measure how far each point is away from the line, square it, and we want that squared value to be the smallest possible. If it's the smallest possible, then it's as close, all the points are as close to the line as possible. So here's a line with a bunch of data points. And what's listed here is the distance that each of those points is away from that line of best fit. That vertical distance from the point is called the residual. If the residual is positive, the point was above the line. If the residual is negative, it's below the line. And if the residual is 0, that means that the point is right on the line. If we square all the residuals and add them up, and it's the smallest possible, then you have the best estimate for your line of best fit ever. Now, how do you go about that? Right? Do you draw one, count all the squares, and then just guess and check forever? No, we're going to want to have a systematic way of doing that. The nice thing is, though, we generally use technology. Technology has it built in to do it because the formulas are wonderful looking. Don't those look nice? The slope of your line should be this, sxy over sx squared. So statistics is notorious for having formulas that do not look nice at all. So the formula for the slope doesn't look nice to begin with, but then the equations for figuring it out are not nice even within it. So sxy is the sum. You multiply all your x coordinates and y coordinates together, add those up, then subtract adding up all your x coordinates separately, multiplied by adding up all your y coordinates separately, divided by how many you have. And sx squared is just adding up all the squared x values, squaring the total if you added up the x values separately, divided by how many you have. Where did someone come up with this as an idea? So let's look at a very simplistic little example. We have only 3 points, 1, 3, 2, 1, and 3, 5. The red line is going to be the line of best fit. 2 of the points are above, and 1 is below. Can you see if I make it steeper, that I get closer to the r gets smaller, but p would get bigger? And so where exactly should you have this line of best fit? And with 3 points, there would be a lot of differences if we drew it by eye. Okay? First of all, you have your x values and your y values. Those are our points listed. I can multiply x times y, 2 times 1, 3 times 5, 15. I can square x, 1, 4, and 9. If I sum things up, this would be the sum of x's, this would be the sum of my y's, this is the sum of x times y, and this is the sum of x squared. Plug these things into our formulas. The SXY formula says sum of xy, that's our 20, minus the sum of x times sum of y, 6 times 9, divided by how many we had. We get 2. And the sum of x squared is adding up all the x squareds, which we figured out was 14. I've got the data here again. Sum of x, which is 6, all squared would be 36, divided by 3. We calculate that to be 2. We take those two things and divide it, and we find out that our line of best fit should have a slope of 1. We can also calculate the mean point to be 2, 3, same way as before. What's the average of your x values? Add them up, divide by 3. Average of your y values, add them up, divide by 3. You would get 2, 3. And so our line of best fit should be y equals x plus 1. And that's a mathematical way, and if we've done it that way, that guarantees that those residuals are the smallest possible that could have existed. Again, what led someone to figure this out, we're not going to go into. But it's pretty impressive, especially if you had, like we just did 3 points, but if you had multiple points, it would work. So we know how the formula works. If you had multiple points, do you see that this chart would just get more and more complicated to fill in? There'd be a lot of things to fill in. Then you'd go to your formulas and have to fill in a lot of things. So this is set up to be done in our graphing calculators. So if you take our graphing calculators, we're going to enter in just these 3 points, right? 1, 3, 2, 1, and 3, 5. Just something simple. So we hit our stat button. My calculator is frozen. Enter your data into list 1 and list 2, x values into list 1, y values into list 2. So if we had 1, 3, 2, 1, and 3, 5. We could put those data points in. Some things on your graphing calculator. If I want to create a scatter plot for this, I hit the second button and y equals. And number 1, push enter. Right now, I have my box and whisker plot turned on. So if I go and push enter on the dot part, that is my scatter plot. I want my x list to be in list 1, my y list to be in list 2. And if you hit the zoom button and go to number 9 for zoom statistics, those 3 points should appear. If you don't like the window with zoom statistics, you can still go to your window button. I might go from -1 here, -1 up to, sure, 3.2. And my y min, I might go to -1 as well, just so I can see my axes, because sometimes it's nice to see your x-axis and y-axis. Sometimes it's nice if your computer doesn't freeze in the middle of your lesson. Just sometimes. Usually, it's quite enjoyable. But since it's Friday, I'm not enjoying that it's freezing. So if I change my windows x min to -1 and y min to -1, now I can see the x-axis. So how do we calculate the line of best fit with our graphing calculator? We figured it out to be x equals 1. We can hit the stat button. And then across the top, if we arrow over to calculate, it has a whole bunch of regressions, right? It has a linear regression, quadratic regression, cubic regression, quartic regression. We're going to start with the linear one, number 4. We have our list 1. We have our list 2. Okay. Again, some of you have older calculators. When you did linear regression, all that appeared on your screen was linreg. Okay. Then you have to go list 1, comma, list 2, and push enter. The nice thing about this version is I can store my equation into y1. And I'll show you, if you hit the variables button, VARS is variables button, and then go over to y variables, push enter on function, then it has y1 up to y9. I'll just pick y1. On the older calculators, you'd have to put list 1, comma, list 2, comma, y1. So, and you would find the y1 in the same place where you go to variables, over to y variables, function, y1. Now, when we push calculate, it finds ax plus b, a is 1, b is 1. If I go to y equals, it stored 1x plus 1 in there for me. Okay? If I go second enter, this is what you would type in if you don't get that sub-menu. So this is what it would have looked like when you were typing it in. If you have a TI-83 or a TI-84 that is a little bit older, then I would say come update it, because you can update the TI-84s. This is what you would put in to figure out, and it figures out that a is 1 and b is 1, and it stores it into y equals x plus 1. So now when I graph, not only do I have those 3 points, I also have my line of best fit graphed as well. Which means I can use that line to figure out all sorts of things. Like, for example, if x was 1.5, second, calculate a value when x is 1.5. Push enter. And I did something wrong. No, 1.5, not 105. That's what I did. It finds out that, oh, y should be 2.5, which makes sense since the formula was x plus 1. So, I'm going to get you to try this one on your own. Put the data point into list 1 and list 2. Come up with the equation from your calculator. All right. Did your scatter plot look like that? Did you get approximately 0.117x plus 83.3? How do you get that? So you're going to have to, once your data points are in, okay, you're going to go stat. So on your calculator, I still have the old data points in, but I'm going to go hit my stat button, go over to calculate, and then the fourth one is your linear regression. You have list 1, list 2. You can store it into y variable function y1 and calculate it. And this is where it should come up with A is 0.117 and B is 83.3. Then the cost of a 1,000-kilometer flight, you would just have to plug in 1,000 for X, and you get what it is for Y. You can either do it algebraically with your formula or do it graphically with our equation. Yes. Did somebody get this equation? Yes? Okay. Because there's times where I put it in, and I put the wrong number into my calculator, and everybody's like, we didn't get that. But if some people did, this way or this way? So then 264, this is interpolation. It's close. And then you might have to change your window to get this answer. Yeah, so yours is a little bit, it might be 1 point you plugged in wrong.
I don't know. I think this is my calculator because look.
No, the calculator would get the same value.
Look, the R. Maybe okay. Maybe I did something.
Yeah,